All right, guys, this is a pretty great topic we're going to talk about today. We are going to be discussing inverse trig functions. So, as of course you remember, of course you remember, in algebra, what was an inverse function? So an inverse function kind of undoes a function, or if you think about it, you know, if I have some function maybe that graphs 1 to 1 and 2 to 5, maybe 6 to -2, right? If this is my function, then what does the inverse do? Let's make that -1 to 1. The inverse just goes the opposite way. So then 1 goes to -1, 5 goes to 2, right? And -2 goes to 6. So remember that there are a couple things that were interesting about inverse functions. So first of all, some things that we know about f and f inverse. If f has an inverse that is a function, so f has an inverse that is a function, if f is 1 to 1. Is 1 to 1, right? And you might remember that term. We talked about it briefly in algebra. Is 1 to 1, or another way to say that is it passes the horizontal line test. The reason we need that, right, is because remember a function, hold on, I gotta finish writing this first. A function takes every x value and maps it to one and only one y value. So a horizontal line test, right? So an example of a function that's doesn't have an inverse over its whole domain, that is a function, is y equals x squared. So y equals x squared fails a horizontal line test miserably because 2 maps to 4, right? But then we also have that -2 maps to 4. So the problem with that is then what is the inverse function going to do, right? It's going to switch those values. So the inverse then is going to take 4 to 2, but then 4 is also going to go to -2. So this right here is a problem if we want that inverse to actually be a function. If I asked you what does the inverse do to 4, you would not be able to answer me with just one number, right? You would say, well, it goes to 2, but it also goes to -2. And the other reason that doesn't work is if you look at the graph of the inverse, remember the graph of all of our inverse functions, right, are, it doesn't go through that point. It goes through 1, 1, but it's a reflection about the y equals x line right there. There's my y equals x line. So notice if I took this green parabola right here and I flipped it across the y equals x line, there's some really loud people outside of my office right now. And then I tried to do the vertical line test, right? There are 2 spots right there that it hits, more than just 2, but it doesn't pass the vertical line test, so that tells us that it's not actually a function. So what we end up doing in situations like that, like if I were dealing with y equals x squared, I'm going to pause this until these people move out for a minute. Sorry about that. What we do to get around that is we say, okay, well, let's just consider x squared, but let's just consider it over a restricted domain. So I'm going to consider x squared, but I'm only going to look at x greater than or equal to 0. So notice if I restrict the domain of x squared to be greater than or equal to 0, and I take my y equals x line and I flip it across that y equals x line, you see we get the square root of x, and that is the inverse of x squared as long as we're looking over this restricted domain. And notice for the square root of x, right, x must be greater than or equal to 0. So I just wanted to remind you of this because when we look at the inverses of the trig functions, it's clearly that if you look at the graphs of the trig functions, it doesn't pass the horizontal line test. It fails it miserably, right? Because if we look at the trig functions, here's sine. If I look at the trig functions, look at all these spots, right, where we don't have passed the horizontal line test. So we're going to have to deal with that. Before we deal with that, though, the other thing I want to remind you of, get a little bit more ink flow there. One other thing about inverse functions that we want to remember that's kind of important is that the domain of f, the domain of f is equal to the range of f inverse, assuming that f inverse, right, is a function. And then likewise, the range of f is equal to the domain of f inverse. And this makes sense because remember what the inverse function does. The inverse function you're just switching x and y, right? So if your domain values are x, then when I switch them, they'll become y's. So that means that the x's for my function are the y's now for my inverse. And likewise, the y's of my function are now the x's for my inverse. So that means that's the domain. So with all that in mind, it was like 6 minutes of a section that takes like 2 days in college algebra. More than 2 days because you have to find inverses also. With all that in mind, let's talk about the inverse functions for sine and cosine and tangent. So sine. Let's look at sine. So sine, if we think of, now I know we can plug in just real numbers into sine, but I would also like to maybe just think about angles, because that's kind of what we're used to. Whether or not you think of these as real numbers, because we've developed them as angles, I'm assuming that mostly you think of them as angles, even though they're real numbers. So there's my really quick graph of sine. Clearly it does not pass the horizontal line test. So like think about this. We know that, the sine of 0 is 0. We know that the sine of pi over 2 is 1. We know that the sine of pi is 0. So if I were to look at, so this is sine of x. If I were to look at the inverse, so here's what we're going to write for the inverse. We're going to do sine to the -1 of x. Okay, so that little -1, I know normally if it's like sine squared of x or sine cubed of x, that means sine times sine. But we're going to break with notation here a little bit. That -1 does not mean 1 over sine. That -1 means it's the inverse of sine. So what would 0, 0 go to? Clearly that go to 0, 0, right? Pi over 2, this is going to go to 1 pi over 2. But then here, notice we're going from pi to, 0 to pi. So right here, you see we have an issue. Sine inverse now it is not a function, which, you guys, the title of this section is inverses of trig functions, and it could even be inverse functions. They should be functions. So the first thing we're going to do with sine is we're going to restrict its domain, okay, so that when I take these sine inverses, so that I get something that is going to be a function, okay? So let's think about where that domain would be. Remember, sine starts repeating itself, right? So if I look at sine, remember sine goes through all the values from -1 to 1. So I want to make sure that I take a chunk of the domain that gets all of those possible values. For example, if I decided to just consider this part of sine right here, from, let's say, 0 to pi. Notice I'm only getting the values that sine spits out from 0 to 1. I want more than that. I want to get, what is the range of sine? The range of sine is -1 to 1. So I want to make sure I get all of those values. And I also want to make sure that that I pick maybe an interval that isn't too choppy. We're going to see we're going to have to chop it up a little bit maybe when we get to some other ones. But for sine, what we're actually going to restrict sine to is I'm going to take everything from -pi over 2 to pi over 2. And I'm going to restrict that graph. So when I am talking about inverse sine, I want to think about if sine just didn't exist over here, okay? What if sine was just this guy right here? Notice I get all of the values from -1 to 1, right? I get all those possible values. So all I'm doing is restricting this domain a little bit so that I just consider values between -pi over 2 and pi over 2. If I do that, you'll see if I take this guy and I reflect it about the y equals x line, now I have to think about this a little bit, which is sometimes hard for me to do. But it'll do something like that maybe. So if I look at the y, that's not exact. They shouldn't quite match right there. But I have a function. Notice that purple line, if you can kind of see it, is a function. So sine inverse. Sine inverse, we are going to restrict between -pi over 2 and pi over 2. So look at, this is -pi over 2 right here, and this is pi over 2 right here. So sine inverse, we are going to get rid of anything that is not between these two. And I just saw my mistake. You guys saw it like 10 minutes ago. This is pi. So sine inverse would never spit out this number pi because we're not going to consider any values between pi over 2 and 3 pi over 2 basically, okay? So we are only going, sine inverse will only spit out values in the first quadrant or the fourth quadrant. Now, I want you to use the notation negative pi over 2 to pi over 2. So your answers, even though, negative pi over 2 is coterminal with 3 pi over 2, it wouldn't make sense to say 3 pi over 2 to pi over 2. That just really doesn't make sense to go that direction, right? Because we go this direction. And if we go negative pi over 2 to pi over 2, when we look on the graph of sine, we can see that that is a nice interval. Whereas if you told me it was from 3 pi over 2 to pi over 2, that doesn't make sense. 3 pi over 2 is this way, and then pi over 2 is all the way over here. Okay, so when we talk about sine, we're going to restrict sine to quadrants 1 and 4. You can think of it that way, but I want you to realize that any angle that you put in quadrant 4 must be written as an angle between negative pi over 2 and 0. Okay, so that's sine inverse. I think we'll just write these all down here in a second. Cosine, let's just kind of show you what cosine's going to do. Here's cosine. Oh man, that was a horrible cosine. Oh my goodness. Sorry about that. That's a horrible cosine, but that's all right. So remember, same thing with cosine. I want to get all the values of cosine. I want to get the positive and the negative. So I don't want to do the same. So negative pi over 2 to pi over 2 for cosine would be this part of cosine right here, that purple part. That's not going to work because I don't want to, that would only give me values of cosine between 0 and 1. I want more than that. I want between negative 1 and 1. I'm going to get all the values of cosine. So for cosine, we're going to grab all of this, and then I'm going to grab all of this, and then it would just start repeating itself, right? So for cosine, we're going to squish cosine here between 0 and this right here is pi. So if you notice, I get all the positive values for cosine, all the negative values for cosine. So what quadrants is that for cosine? So cosine is going to take cosine inverse, is going to spit out values between 0 and pi. Cosine's pretty nice. 0 to pi is just going to be this right here. So quadrants 1 and 2. Notice these quadrants kind of make sense. If you look at cosine, whereas cosine's positive in the first quadrant and negative in the second. So I get all possible values for cosine. Same thing with sine. Sine is positive in the first quadrant, negative in the fourth quadrant. So I get all possible values. Whereas again, if I had taken 1 and 2 for sine, do you see how I would only get positive values for sine? So I wouldn't be able to take sine inverse of anything that was negative, which we know isn't true. And then we'll see tangent is going to be the same as sine. We just can't actually take the y-axis. I feel like I'm rambling a little bit. I'm sorry about that. So let's just write this all down. And then, of course, we're just going to do, we're just going to do a bunch of examples. Let's do it. Okay, so the inverse trig functions. Let me actually get a pen. So again, what I mean by restricting, I'm restricting, so think about this again. I'm restricting the domain of sine. What does that mean then for its inverse? Remember, I'm only restricting it when it comes to the inverse. So the domain of sine is the range of the inverse. So remember, that means that the range of the inverse function is restricted, okay? So the first one here, let's talk about sine. Let me make sure I get everything that your book wants. Okay, so first, let's look at y equals the inverse sine. One other way that you're gonna see sine written sometimes is we call it arc sine. I don't actually know the history behind the arc sine. My guess is it's a way to get around doing that -1. But if you see arc sine, that just means the same as inverse sine, okay? So what does arc sine mean? So remember, if I have y equals the sine of x, right? Remember how we found inverses? We switched x and y. That's what we did back in the day. That's what inverse function did. And we know that's what inverses do. It switches x and y. So y equals the sine inverse of x. What does that mean? It means x equals the sine of y. So let's think about that for a minute. So what is the inverse going to do? It's going to spit out angles. I know they're not angles, they're real numbers, but for you to kind of think about what that means, look at, we have y equals sine inverse of x, which is the same thing as x equals sine of y, okay? So what this is going to spit out, that y is an angle. Notice I take the sine of some angle and it spits out a number. The sine of 45 degrees is root 2 over 2. We're just going the opposite way now. So I'm going to take the inverse of root 2 over 2. What angle does that equal? Let's write this all down and then we're going to do a bunch of examples, okay? So sine inverse, couple things here. The domain, remember, we switch our ranges and domains. Remember, the range of sine is -1 to 1. That means the domain of sine inverse is -1 to 1. Okay, so remember that they switch. And then the range, remember we're restricting the domain of sine. What are we restricting the domain of sine to? We're going to restrict it from -2 pi over 2 to pi over 2. So because we're restricting its domain, that restriction is going to go on to the range for sine. So that is -pi over 2 to pi over 2. Another way to think of that is that sine inverse will only spit out angles in quadrant 1 or 4. Okay? -pi over 2 to pi over 2, right in here. Cosine inverse. Cosine inverse of x, which is the same thing as arc cosine of x, which is the same thing as what angle do I get when I take the cosine of y, right? Or I'm sorry, yeah, what angle do I get when I take the cosine of, what angle do I get when I take, I need to stop talking, you know what I mean. What is the angle that I get when I take the cosine of it and I get that value x? Oh my gosh, I'm so sorry. We need to just do some examples because I think I'm just making this worse. Domain's still -1 to 1. Remember, that's the range of cosine, so that's the domain of my inverse. And then the range, we are restricting cosine to be in quadrants 1 and 2, so 0 to pi. You guys are just going to have to memorize these. Kind of trig is a lot of memorization. You're going to have to memorize where these inverse functions live. Tangent inverse, or arctan. Same thing, x equals the tangent of y. So it spits out angles. So one thing on this one, think about what tangent looks like. I'm going to go up here. Tangent looks like this, right? It goes like this, where it has a vertical asymptote at pi over 2. Look at what the range is for tangent. It's -infinity to infinity. So that's going to be the domain of inverse tangent, okay? -infinity to infinity is the range, so that's the domain now of inverse tangent. With sine inverse and cosine inverse, we can only plug in values between -1 and 1. That's not true with tangent inverse. Tangent inverse, I can plug in any value I want. And then let's do the range right here. Well, it's pretty, I remember I want all the values. I want -infinity to infinity. Clearly, tangent's a pretty easy one to, it doesn't pass a horizontal line test, but what if I just got rid of all of these things over here and just looked at one of these little squiggly things? That's a mathematical term, squiggly things. Then that range would be from -pi over 2. Now, I can't include pi over 2 like I could with sine. -pi over 2 to pi over 2. Again, that's quadrants 1 and 4. So it's a lot, it's just like sine that doesn't make sense, but whatever. The y-axis, no y-axis. Okay, sine I can grab. Sine inverse will spit out values on the y-axis. Tangent inverse won't, because the tangent of pi over 2 is undefined. So I can't take tangent inverse of the number undefined. That doesn't make any sense, right? All right, cool guys. We need to do some examples because I feel like I haven't actually conveyed these super well, but let's go ahead and do some examples so you can kind of see what I mean by all of this. These actually are a really good time once you get going. I'm sure you believe me. So the example, just going to do examples for evaluating this stuff. So let's evaluate, and this will be on a non-calculator part of the test, something like sine inverse of root 2 over 2. Okay, so let's think about what this is asking. So remember, sine takes angles, right? And not necessarily angles, but it could just be real numbers, and spits out a number. So that's what sine does. So what would the inverse function do? Remember, it goes the opposite way. It takes a number and it spits out angles, aren't real numbers. But anyway, angles, let's think of them as angles. So remember sine inverse. Sine inverse, if we look at where we have restricted sine, we restricted sine to be between negative pi over 2 and pi over 2. So that means that sine inverse is only going to spit out values. That's its range now. It will only spit out values between negative pi over 2 and pi over 2, okay? So let's think about root 2 over 2. So here's how I usually do this. I look at my coordinate system and I think about where sine inverse spits out values. Sine inverse will spit out values between negative pi over 2 and pi over 2. Okay, so in quadrants 1 and 4. The next thing I look at is the value that I'm taking the sine inverse of positive or negative? Because that's going to tell me which quadrant it's going to lie. So I'm going to look at quadrant 1 or quadrant 2. Well, this is a positive number. Sine is positive in 1 and negative in 4. I keep saying 2. I'm so sorry. I meant 4. So I know that whatever my angle is going to lie in quadrant 1 here. So what angle, when I take the sine of it, gives me root 2 over 2? That's in quadrant 1. That would be pi over 4, or 45 degrees, right? Notice if I rewrote this, and if I take this guy right here and I get rid of that sine inverse, so the minute that sine inverse goes across the equals sign, it becomes a regular sign. And sure enough, notice sine of pi over 4 is root 2 over 2. What if this one had been sine inverse of a negative root 2 over 2? Okay, then again, I'm looking at my quadrants. I know sine inverse spits out values in 1 or 4. I know that sine is positive here and negative here, and this is a negative value. So I know I need to find an angle in the 4th quadrant, right? And I don't want it to go all the way around, right? I want it to stay in the 4th quadrant. So I need an angle that does this, a negative angle. And what would this be? Well, my reference angle must be pi over 4. So to get it into the 4th quadrant, it must be a negative pi over 4. Okay, so this is a negative pi over 4. The nice thing about sine inverse, I'm going to just tell you right now, if you find its reference angle, just put a negative in front of it. That's going to put you into the 4th quadrant if it's negative. So that's actually pretty nice with sine inverse, because the minute you put a negative in front of it, it's just going to throw you into the 4th quadrant. All right, so let's look at an example with some other ones. You know, what else are we going to do, right? So what about cosine inverse or arc cosine? Okay, of let's say 1/2, and then we'll look at a negative 1/2. So cosine inverse, again, I'm going to think about, what is this asking? This is asking what angle has 1/2 when taking its cosine, right? That's what it's cosine. Or the cosine of what angle is 1/2. So 1/2, that's positive. So again, I'm going to kind of draw my quadrants. I know that that cosine inverse, its range is 0 to pi, so it's going to spit out angles between 0 and pi. So what quadrants is that? That's quadrant 1 and quadrant 2, right? So anything in here, including the axes, that's okay. So first off, I need to figure out my reference angle. So however you do that, if you use the unit circle, or I know I've shown you how to use it. I do the little chart, right? So I'm going to look at my chart and I'm going to go down to my chart and I'm going to find, I'm going to go at cosine and look over where it's 1/2. And if you remember that, we know that the cosine of pi over 3, right, is 1/2. And this is a positive 1/2. So I'm going to take cosine is positive in the 1st quadrant, negative in the 2nd quadrant, so pi over 3 must be my angle. So that is the cosine inverse of 1/2, okay? What about cosine inverse of a negative 1/2? So remember, I said that trick with sine, you just put a negative in front of it, right? This is not true with cosine, people. Heed my warning. Cosine inverse, this is not true. If I decide, let's say I'm getting crazy, I know, and I say, okay, the answer is a negative pi over 3. Well, let's think about that. And I'm asking a lot. I'm asking a lot for you to think about it. But let's think about what that would mean. So negative pi over 3, remember negative pi over 3 means I'm just coming the opposite direction, right? So this angle right here is a negative pi over 3. But people, cosine is positive in the fourth quadrant. Cosine is positive in 1 and 4 because cosine are our x values, and x is positive in the fourth quadrant. So the cosine of a negative pi over 3, my friends, I don't know, I think friends. The cosine of a negative pi over 3, my friends, is not a negative 1/2, it's positive 1/2. So we know that that can't be the answer. We also know that can't be the answer because cosine inverse will never spit out an angle in quadrant 4. Cosine inverse will only spit out angles in quadrant 1 and quadrant 2. Okay, so cosine inverse of a negative 1/2 then. I know I'm going to be in quadrant 1 or quadrant 2. I know that my reference angle is pi over 3. So what I want then is I want an angle in quadrant 2, right? Because that's where cosine's negative, and I know that this is negative right here. I want an angle in quadrant 2 whose reference angle is pi over 3. What angle is that? Well, I know that pi would be 3 pi over 3. So it's 1 pi over 3 away from pi. So that's going to be 2 pi over 3. Okay. I hope that makes sense. Let's do some more. What else are we going to do? Like not do math? What a sad, sad life that would be. What about tangent inverse of a negative 1? Okay, tangent inverse. So tangent inverse is going to spit out angles in quadrants 1 and quadrant 4, but not going to do pi over 2. Okay, so any angle in here or negative pi over 2. It basically grabs everything except the y-axis because tangent's undefined on the y-axis. So tangent inverse of a negative 1. So tangent's positive in the first quadrant, negative in the fourth quadrant. It will not spit out angles between 2 and 3. That's how we have defined these inverse functions to work, right? So that they are functions. And your calculator also, remember in your calculator when we've kind of dealt with sine inverse and cosine inverse before, which drove me nuts that your book used those functions without actually telling you that they only exist over a certain range, whatever. But we actually, remember we had to like add them to certain angles or to 180 or subtract them from 180. And it was because of that. Your calculator is only going to spit out angles in 1 or 4. So if we actually want an angle in 2 or 3 whose tangent is, negative 1, we'll have to kind of mess with it a little bit. All right, what's my reference angle? Well, I know that the tangent of pi over 4, right, is 1, but it's negative. So I want an angle in quadrant 4 whose reference angle is pi over 4, but is in quadrant 4 is between negative pi over 2 and pi over 2, and so it'd be a negative pi over 4. So tangent inverse has that same trick as sine, where if this is a negative right here, if you find the reference angle, just put a negative on the reference angle, and that throws you into the fourth quadrant. It's actually pretty great. What if I had, arc sine, which is the same thing as sine inverse, but just for fun, we'll do like arc sine of 0. This is kind of interesting, right? So again, I'm just going to think about sine. Arc sine's going to spit out in 1 and 4. And then remember your sine are your y values. So if I think about my y values, where are my y values 0 in between negative pi over 2 and pi over 2, right? In this area right here, it's going to be 0 right there. So the arc sine of 0 is 0. Remember, sine of pi is also 0, but this is a function, and so it's going to be 0. Likewise, what if I had like arc sine of negative 1, right? Where is y negative 1? It would be down here. So arc sine of negative 1 would be a negative pi over 2. Okay, sometimes those can be a little bit tricky. What about cosine inverse of 0, right? Cosine inverse is 0. Where is cosine 0 in quadrant 1 or 2? Cosine are your x values. So if I'm looking at this area right here, kind of drawing a unit circle here a little bit, where is x 0 anywhere in here? It's 0 right there. So that would be pi over 2. Cosine inverse of negative 1, if you look on that same thing, would be pi. I hope that makes sense. You can also do this on your calculator. On your calculator, I'll let you, that's not too hard to figure out. You have a sine button, and then you'll do the second button, and there should be a little sine inverse button on the top there. So you can do this, and if you're in radians, it'll spit out in radians. If your mode is in degrees, it'll spit it out in degrees. And you'll see that your calculator will only be spitting it out into quadrants where sine inverse, tangent inverse, and cosine inverse are going to spit out their angles. One other quick little thing. I want to write down really quick. We do have inverse functions for the reciprocal functions. Okay. So, if we add that to, did I get rid of it? I don't know. I think I did get rid of it. Yeah. No, okay, there we go. So let's add that to kind of our list here. So we're at 3 with tangent. So let's go ahead and bring in, let's bring in the reciprocal functions. So 4 here, cosecant inverse, that's just the inverse of 1 over, that's 1 over the inverse of sine, right? That's what cosecant inverse would be. If we look at cosecant inverse, its domain, okay, so if you remember what cosecant looked like, cosecant looked like this. It had vertical asymptotes, and this was 1 and this was -1. Had vertical asymptotes, okay, at 0 and pi. So look at the range on this guy. The range on this is 1 to infinity and minus infinity up to -1. So that means that's going to be the domain of cosecant inverse. Remember, the domain is just the range of the function itself. Okay, and then actually the way we're going to split up cosecant, it's going to be very, very similar to sine. I still want quadrants basically 1 and 4, except I can't take the cosecant of 0 because that would be the sine of 0 is 0, and then it'd be 1 over 0, and we know that's bad. So for cosecant, if you notice, what we're kind of grabbing here is we're going to be grabbing this part here, -pi/2 to 0, and then this part here. Okay, and if you notice on this graph, that kind of makes sense. So this is pi/2, so 0 to pi/2, that's quadrant 1, -pi/2 to 0, right? That's quadrant 4, and then of course we can't hit 0. So secant, y equals secant inverse of x. So same thing, my domain's going to be the same. And secant inverse, I'm going to tell you, sometimes, actually with cosine also, I have seen some books define it a little bit differently with the ranges, but I'm just going to, of course, go with what your book does. So secant, I'm also going to use 1 and 4, but then where is cosine 0 at pi/2, and I can't take, don't put a closed bracket. Oh my goodness. We're going to do pi/2 to pi, right? Because secant is 1 over cosine, and cosine of pi/2 is 0. So secant inverse will also spit out angles in 1 and 2. It just won't spit out anything on the y-axis there. And finally, cotangent inverse. If I look at cotangent inverse, the domain of this guy is all real numbers, or minus infinity to infinity, just like tangent, right? Cotangent is very, very similar to that. So the range on cotangent is going to be a little bit different because if you looked, remember, at cotangent, the graph was very, very similar to tangent. I believe it went like this. Oh man, don't maybe quote me on that. But if we want to get one nice little section, right, of cotangent, I'm going to restrict its domain to just be 0 to pi. It's just a nicer way of grabbing it. I could do 1 and 4, but then if I did 1 and 4, if you look at 1 and 4, I would grab this part and then I would grab this part. And so it's just easier to do 0 to pi for cotangent. Okay, so for sine, cosine, and tangent, you need to know those quadrants where the range of those quadrants for sine inverse, cosine inverse, and tangent inverse. If I happen to ask you about maybe cosecant and secant and cotangent inverse, I'll probably give you those ranges just because they're maybe not used quite as much as we use that for sine, cosine, and tangent. So, all right, you guys, one more quick idea. Well, kind of quick idea about this, and then we'll call this good. So the composition. So composition of inverse functions is kind of an interesting thing. I want to write this down really quick, and then we're going to do a bunch of examples, okay? So remember, when we compose inverse functions, they undo each other. So one way that you can verify two functions are inverses, wow, that's a crazy one, is that when I, first do f inverse and then do f, I get x. Or the other way, when I first do f inverse, or first do f, remember read right to left, and then do f inverse, I get x. But when we do this, we're assuming something that we don't really drive home in algebra. When I take f inverse of x, that x right there, you guys, has to be in the domain of f inverse, and then I apply f. Same thing here, if I apply f to x, that has to be in the domain, and then I apply f inverse. So whatever we apply out here, that also must be in the range of f inverse. Same thing here. Okay, so let's write down these rules for composition, and then I'll kind of explain where this is coming from and why we need to even kind of worry about this. So let me get back to where I wanted to be. There we go. So if I take sine inverse of x, inverse of x, okay, these guys are gonna undo each other. If I take the sine inverse of x and then take, oops, let me get rid of these really quick so I have some room. They're going to undo each other, and I'm gonna get x out, and that is going to be true as long as x is in the domain. I'm gonna put an element of, if that's all right, the domain of sine inverse of x, or just sine inverse, let's say. And that would make sense, right? Because look at what's going first. Sine inverse is going first, so as long as that x is in the domain of sine inverse, then the sine of that will be x. And I'll show you why that's true here in a minute. So these inverse functions, they do undo each other as long as we're playing nice, okay? So I'm gonna say here also for x that is an element of the domain of, I'm being really lazy now, cosine inverse. And then tangent also, if I compose tangent, now remember again, and not to belabor the point, but which function's going first? Tangent inverse is going first. Remember, what is the domain of sine inverse and cosine inverse? It's negative 1 to 1 because it's an inverse function. The domain of tangent inverse is all real numbers. This is for x, an element of the domain of tangent inverse. Okay, so for example, if I had, sine of the sine inverse of the square root of 3 over 2, this will just spit out the square root of 3 over 2. And let me show you why that's true. And we're going to add to this, by the way, I should have told you that. Here, let's work from the inside out. Sine inverse of root 3 over 2. Sine inverse spits out angles in 1 and 4. I know that the sine of pi over 3, right, is root 3 over 2, and it's positive. So I know that I'm going to be in the first quadrant, so it'll be pi over 3. So this whole inside thing, what is sine inverse going to spit out? It's going to spit out pi over 3. And then what am I doing now? I'm taking the sine of pi over 3. But what is the sine of pi over 3? Well, we just talked about this. This is root 3 over 2. So that makes sense then, that if I'm taking sine inverse of pi root 3 over 2, I'm spitting out an angle whose sine is root 3 over 2. And then when I take the sine of that angle, it best be root 3 over 2. Okay, so that's what we know. We also, and you can like if I asked you to take tangent inverse, remember tangent inverse, its domain, tangent inverse's domain is all real numbers. So I could take tangent inverse of 1024. Right? I don't know what tangent inverse of 1024 is. It doesn't matter. I know that they're gonna undo each other. Okay, so this is a great, well, I don't know. Maybe we differ on what's great and not. But this is a really great thing with composition. Okay, so that's if you're applying the inverse function first. Or what if I asked you to take, sine, or let's say cosine? They'll try and trick you. And by they, I don't mean me. Of course I don't mean me. What if, well, probably not. What if I asked you to take cosine of cosine inverse of 2.4? Is that going to be 2.4? No, guys, it's not. This is undefined. There's no solution to this because cosine inverse of 2.4 doesn't make sense. I can't find an angle whose cosine is greater than 1 because cosine always is between -1 and 1. Okay. All right, though, let's look at the other way. So this is the one that's going to be a little bit more tricky. So another composition, but looking the other way. So I'm going to write this down and then I'm going to explain to you why this is true, okay? So if we go the other way, sine inverse of the sine of x, these guys will undo each other, but the only way that this is going to be x, right? The only way that the input is also going to be the output is if x is in the range of sine inverse, okay? So what I'm saying here is if this value right here is not in quadrants 1 or 4, we have more work to do, okay? It's not going to be that same one. So we'll do some examples here. Cosine inverse of cosine of x equals x. This is only if x is in the range of cosine inverse. And we know the range of cosine inverse, right, is quadrants 1 or 2. And then similarly, tangent inverse of tangent of x, it will just spit out that same value of x as long as x is in the range of is in the range of tangent inverse. Okay. All right, you guys. So let's look at some examples, because the thing is I'm going to give you problems where that number is not in the range. And so we're going to have a little bit of work to do, okay? So for example, let's say that I want the cosine inverse of the cosine of 2 pi over 3. Okay, you guys, this one's all right. This one is going to spit out 2 pi over 3. How do I know that's going to spit out 2 pi over 3? Because I know that cosine inverse is only going to spit out angles that are in quadrants 1 or 2, right? And 2 pi over 3 is 1 pi over 3 away from pi. So I'm in quadrant 2, so I'm good to go. Let me show you why this is true really quick. What is the cosine of 2 pi over 3? Well, that is a reference angle of 60 degrees, right? Pi over 3. So I know that this value right here is a negative 1/2 because 2 pi over 3 is in the second quadrant. And I know that the cosine inverse of a negative 1/2 is 2 pi over 3, right? That's just kind of doing what we did before. But guys, what if I asked you, what is cosine inverse, right, of, let's say, the cosine of 5 pi over 3? The solution is not 5 pi over 3. In this case, this does not work. Now, the 5 pi over 3 works because because that's in the domain of cosine. But remember, we restrict the domain of cosine when we define the inverse functions. So we cannot just spit out 5 pi over 3 in this case. That would be the incorrect answer. If you put this into, so 5 pi over 3 is 300 degrees. If you put this into your calculator and did cosine inverse, the cosine of 300 degrees, you will see you will not get 300 degrees out. Cosine inverse will never give an answer that is outside of quadrants 1 or 2. Okay, so we need to be in quadrants 1 or 2. So let's work this out and let's see what we get. So cosine of 5 pi over 3, right? 5 pi over 3 is almost to 6 pi over 3. 6 pi over 3 is 2 pi, right? That's 6 pi over 3. So I'm a pi over 3 away from 2 pi. So the reference angle is 60 degrees, or pi over 3. I know that the cosine of 60 degrees is 1/2. I'm in quadrant 4. Cosine is positive in quadrant 4. So I know all of this under here is 1/2. So I'm going to replace that 1/2. Or I'm going to replace cosine of 5 pi over 3 with 1/2. And now I have a whole new problem to do. Now I have a new problem where it says, okay, find the cosine inverse of 1/2. Where is cosine inverse defined? Cosine inverse not defined. Where does it spit out angles? Cosine inverse spits out angles in quadrants 1 or 2. 1/2 is positive, right? So I know that my answer is going to be in quadrant 1. I know my reference angle is pi over 3, guys. That's what we've been dealing with, right? So my reference angle and my angle itself are the same thing in quadrant 1. So what is the answer? Pi over 3. Okay, so notice how they didn't just undo each other, right? I had to spit out an angle that I know is in the quadrant where cosine inverse spits out angles. Let's just do a couple more. I know I'm at 45 minutes, so I think we'll be about done here. But what if we had, let's say, the sine, inverse sine of the sine of 7 pi over 6. Okay, it's not going to be 7 pi over 6. It can't be. 7 pi over 6 is pi over 6 away from pi. Remember, pi in terms of pi over 6 is is 6 pi over 6, and I'm one more than that. So I'm just going to work on from the inside out. So this guy right here, what's my reference angle? My reference angle, right, is pi over 6. I know that the sine of pi over 6, that's 30 degrees, that's 1/2. However, I'm hanging out in the third quadrant. So everything's negative except for tangent in the third quadrant. So the sine of 7 pi over 6 is a negative 1/2. So I'm going to replace this stuff in the parentheses with a negative 1/2. And then I know my reference angle is still pi over 6, you guys. Sine inverse spits out angles in 1 and 4. How do I get it into the fourth quadrant? Remember, that's the easy one. We just put a negative in front of that pi over 6. I hope that makes sense, you guys. You got to let me know if it doesn't. We can also have more fun with these if we want to. I mean, I could even do something like we can put these together. This isn't a composition one, but these are just kind of fun to do. I know my idea of fun and your idea of fun is different. What about cosine, tangent of the cosine inverse of a negative, I want a negative, of a negative root 2 over 2. Oh, these are just fun to work with. So let's look at the inside here. So I'm going to mess with this first. So cosine inverse of a negative root 2 over 2. Cosine inverse spits out angles in quadrants 1 or 2. Cosine is positive in the first quadrant, negative in the second quadrant. So I know I must be in the second quadrant because of that negative sign. What angle, when I take the cosine of it, gives me positive root 2 over 2? That's pi over 4. So my reference angle is pi over 4. So what is this angle right here? Well, if we're at 4 pi over 4 here if we're at pi. So I'm a pi over 4 away, a pi over 4 away from pi. So that would leave me with 3 pi over 4. Okay, so that inside function is, or inside value is 3 pi over 4. So this leaves me with the tangent of 3 pi over 4. Okay, I know the reference angle is pi over 4. I know the tangent of pi over 4 is 1. In the second quadrant, tangent is negative. So this guy actually spits out a negative 1. That's pretty crazy, huh? I like that one. Okay, one more example. I said we were doing 2 more, but now we're going to do, that's 3 more. So we're going to do 1 more, and then I promise I'm going to leave you alone. What about something like this? I love doing ones like this. What about the cosine of the sine inverse of a negative 4/5? Okay, so I want the exact value of this. And you're probably like, Sarah, you're crazy, which I might be, who knows? But you guys, what do I know? I mean, I probably am. What do I know about this? I know that sine inverse spits out angles, right? So I'm going to call this theta. I'm going to say that theta equals sine inverse of this negative 4/5, right? I know that's what sine inverse does, is it spits out angles. And if I rewrite this, this tells me that sine of theta equals a negative 4/5. Guys, I've been giving you questions like this for 8 weeks now, right? If I know, and what do I know about theta? I know that theta must be in, well, it must be either in quadrant 1 or quadrant 4. Well, I know it has to be in this interval, right? Between negative pi over 2 and pi over 2, because sine inverse only spits out angles in that interval. And it's negative. So what do I know about theta? I know that theta, right, is this angle right here. This is my theta. And I know that its sine is a negative 4/5. So I know that this must be negative 4. This must be 5. And what do I know about this, guys? That must be 3. So why did I do that? Well, because this whole purple thing is theta. So what is this question asking? It's asking, what is the cosine of theta? Well, in this case, now that I have my triangle, because this is theta, I don't know what theta actually is, and I don't need to know it. What would the cosine of that theta be? It'd be 3/5, right? Just by creating my triangle. I don't know if you guys care about what I like or what I don't like. Maybe you should care, but I like problems like that. I think that's kind of fun, and you'll see in your homework, like there's some fun stuff that where you can even like put this together with the sum or a difference formula. It's a good time. Oh my goodness, if you're still with me, I'm so proud of you. 49 minutes. Hopefully you took a break in there. I hope you did. I did. Anyway, let me know if you have any questions. The inverse trig functions can be tricky, so take some time with them. I know I say this on every section, but work with them, get to know them, let them be your friends. All right, see you later.